Hello, and welcome to this presentation on a new circuit developed by ST Microelectronics to optimize the price of high-efficiency converters while not compromising on the performance. The presentation provides an overview of the BC² circuit, its applications, and its advantages compared to traditional topologies. First, let's take a look at the application environment. Increased environmental awareness has made energy saving a major selling point for a wide range of applications. Incentive programs such as 80+ have been launched to drive this race toward more efficiency. Any designer working on an electrical circuit must now consider expensive high-performance components such as silicon carbide diodes or superjunction MOSFETs in order to reduce their power losses. The BC² circuit is intended for high-power applications where boost or buck converters are usually used. They can be found in PFC applications inside desktop PCs, servers, or telecom power supplies. BC² can also be implemented in non-insulated DC to DC converters using boost or buck topologies inside solar inverters. Its use improves the cost-performance ratio of these applications. Now, let's look a bit closer at the concept. What is the BC²? BC² topology is patented by ST Microelectronics and can be applied to boost and buck circuits working in hard switching mode inside switched mode power converters. The example here shows a typical boost converter. The main power losses in this type of converter are linked to the turn-on phase of the main switch, TR, and result from the crossing between current and voltage during this phase. The higher the reverse recovery current, IRM, of the boost diode, dB, the higher the losses. The BC² reduces these power losses inside the main switch by adding a small inductance, L, in series with the MOSFET, reducing dLdt at turn-on, so reducing the crossing between current and voltage. However, just adding this inductance is not enough, as it stores some energy that needs to then be evacuated and ultimately re-injected into the load to avoid any useless power losses. To achieve this, a small freewheeling diode, D1, and two auxiliary windings, NS1 and NS2, sharing the same core as the main boost inductance, are added. The two auxiliary windings act as negative voltage sources and reset the energy stored inside the serial inductance, L, once the MOSFET is completely turned on and the boost diode, dB, is off. Finally, an auxiliary diode, D2, is added to re-inject the saved energy into the load once the main switch, TR, is turned off. In a similar way, the BC² topology can be implemented in a buck topology. We are now going to look at the different operating phases of the BC² to understand how the circuit helps save a significant amount of power. Let's consider the first phase as when the boost diode, or dB, is conducting and the switch, TR, is open. The boost diode, dB, sends the main inductor energy through the output bulk capacitor. Diodes D1 and D2 are not conducting. The second phase starts at T0 when the main transistor, TR, is switched on. The voltage across the switch then drops to 0 volts. The current in the transistor increases until it reaches a value equal to both the input current, I0, and the current, IRM, coming from the recovery of the boost diode. This is the moment when the BC² starts to behave differently from a standard topology. Effectively, the variation slope is limited by the serial inductance, L, avoiding any crossing between voltage and current in the switch. The MOSFET turn-on power losses are thus reduced. The current in the boost diode, dB, decreases with the same slope until reaching -IRM. Moreover, just after T0, the intrinsic COSS capacitor of the power MOSFET is discharged in its RDS on. Unlike standard PFC circuits, the voltage applied across the drain is lower because the reflected voltage, VNS2, is subtracted from Vout. This behavior provides the BC squared circuit with an advantage, since at light load, power saving occurs through lower MOSFET switch-off losses too. The third phase starts at T1, when the diode dB is considered off. The boost diode's recovery current, minus IRM, has been stored in the inductor L. At T1, the voltage polarity across the main inductor changes, and D1 starts to conduct. The energy stored in the inductor L starts to be evacuated by NS1 and is sent to the main inductor LB. The current flowing through the diode, D1, corresponds to the energy previously stored in the inductor, L, and drops to 0 amps. The same current is added to the main current flowing through the MOSFET. To guarantee soft switching behavior of diode D1, this current should reach 0 amps before T3. During this phase, the reverse voltage applied to the boost diode, dB, is greater than the output voltage due to the serial auxiliary winding, NS2, hence the need to use specific diodes developed by ST. In the fourth phase, starting at T2, the current in diode D1 has been cancelled and the diode is open. The circuit works as a standard boost topology with the MOSFET on. The current in the MOSFET increases until reaching I1. The fifth phase begins at T3, when the main transistor TR is open. The voltage across the capacitor COSS of the transistor increases linearly through the current I1 stored in the inductor L until reaching Vout. From this value, the diode D2 is biased and starts to conduct, bypassing the current I1 stored in the inductor L to supply the load. At the same time, the voltage polarity across the main inductor, LB, changes, and dB starts to conduct as well. At this point, dB and D2 share the current. The auxiliary windings, NS2, then act as a negative voltage source applied across the inductor L and cancel the current I1 through it. Consequently, starting at I1, the current in diode D2 decreases down to 0 amps, while the current in the boost diode, dB, increases to reach the nominal current at T4. At low line, the BC squared gives a significant advantage due to this current sharing through the two diodes as the conduction losses are reduced. Finally, the BC squared goes back to a normal operating mode. As a relatively complex circuit, the BC squared must be designed according to a specific procedure. The BC squared is implemented in two main steps. The first step is the easier, as it consists of using a simple software provided by ST to calculate the values of the auxiliary components, L, NS1, and NS2. The second step is an experimental step consisting in fine-tuning the values of L, NS1, and NS2 to maximize the efficiency of the PFC. As previously mentioned, ST provides a simple software to obtain the values of the auxiliary components used for the BC squared. All designers have to do is to input the characteristics of the SMPS on which they want to implement the BC squared. The choice of the BC squared diodes can either be done manually or automatically. When running the software, it outputs the circuit design, the value for the components, the stress applied to the components, and also estimations of the power losses compared to a standard PFC using an SiC boost diode. After designing the BC squared according to the component values given by the software, these values must be fine-tuned to ensure that the best efficiency is achieved. The first step in this fine-tuning consists in choosing the right core for the auxiliary inductor, L, based on the value given by the software. The inductance given by the software is a maximum value taking into account the tolerance. The converter efficiency can be improved by slightly decreasing this value. The second step consists in maximizing the efficiency by finding the appropriate value for L through some experimentation. The BC squared must ensure that the PFC works in soft switching mode, whatever the application conditions. This means that the dead times TD1 and TD2 in diodes D1 and D2 should be higher than 0. Unfortunately, the inductance has an influence on these dead times. The third step thus consists in checking that TD1 and TD2 are higher than 0 in all conditions for the L value found in step 2. The fourth step of the fine-tuning procedure consists in checking that the voltage stress across the boost diode is below 530 volts, the diode featuring a reverse voltage of 650 volts. If steps 3 and 4 are not positive, several options can be applied. The inductance of the auxiliary inductor L can be increased, but this has a negative impact on the efficiency. The number of turns for the auxiliary windings NS1 can be increased, but the voltage stress across the boost diode will be higher. Another possibility is to add a snubber circuit to protect the boost diode. Finally, we are going to look at the different advantages of the BC squared. The main advantage of this topology is that it increases the cost-performance ratio of the application. The efficiency is at least as good as with a standard structure using silicon carbide devices, while the price can be divided in half. Another advantage of this topology is that it removes the switching power losses in the MOSFET when turned on. The consequence is that it reduces the junction temperature of the device. When this junction temperature is reduced, the RDS on is also reduced, reducing the forward losses. A positive loop is then triggered. Temperature reductions of up to 16 degrees Celsius have been found compared to standard topologies. This can help to increase the MTBF of the device or can be used to reduce the size of the heat sinks. To summarize, the BC squared is a patented circuit from ST that uses silicon diodes only. It consists of a topology that can be applied to boost or buck circuits and improves their price-performance ratio compared to standard topologies using SiC diodes. Thank you for your attention.